Hello, good morning. Welcome, everyone. My name is Taehoon Lim, and thank you for joining us today. We have our speaker, Bashir Sadjad. He's a software engineer at Google, and we'll be learning about transforming FHIR data for horizontally scalable analytics. Thank you.
Yeah, thanks a lot. Yeah, thanks everyone for coming. There were some issues with sharing a screen, so I will mostly use my slides, but if I need to switch to demo, maybe at some point, if we have time, then I need to stop sharing and then share again. Again, thanks for coming. So the title says, it's basically, the goal of this presentation is to talk about our work, about transforming FHIR data into a format that is suitable for analytics queries, and then basically some talks about how to do the queries, basically. So I am a software engineer at Google. I have been at Google for the last 13 years. Around 3 years ago, I switched to working on the healthcare space specifically, but almost, most of these 13 years I have been working on as a, data engineer or machine learning engineer on, data systems. Before doing healthcare, before doing EHR stuff, I worked on cloud genomics for a while, and then before that, I was doing ads and search data and things like that. But if I want to just summarize most of my work at Google, it has been, data engineering basically. And before Google, I was working on software for rational drug design, both in my previous company and also in graduate school. Okay, so the goals of today, the presentation, it's basically in one sentence, it's basically to do analytics on FHIR data in a way that is efficient and horizontally scalable, which we will talk about it. And it has two main parts. One is basically to transform the data into a format that's suitable for doing analytics, and then the other piece is how to query that data, basically. Before going into the details of this presentation, so I like to talk about my bigger team. So we are part of, in Google, different teams work in the healthcare space. And our team is called Open Health Stack. We are part of Health AI. So what we do is basically focus on we try to identify problems that are general enough, such that we can contribute an open source solution to it, and it can, especially in the context of healthcare in developing world, in low resource environments, basically. So we are a small team, but we work very closely with our partners, who basically those are the implementers. So they take the components that we build, and then they use it in their deployments, and those are the real the real feedback actually comes from them. So we have three main components right now. The first one is Android FHIR SDK, which is probably the most mature component that we have. Jing, who is here, is the engineering lead for that product, and he has a Let's Build session tomorrow as well. So it's basically, if you want to build FHIR native apps on Android, you can use this library, and it solves many problems that you may have, like some offline support and syncing with a server and all of those. Then we have, so I have worked mostly on the next two components. The first one is the FHIR Gateway, which is not the topic we are going to talk about today. It's basically like a reverse proxy sitting in front of any FHIR server, and then to apply access control. So it talks to a identity provider, and then OAuth, and then you have some logic for access control. So it applies that logic basically when the queries go to the FHIR server. And the third component, which is the topic of this presentation, is FHIR data pipes, which I'm going to talk about it in details. Okay, so a little bit of background about FHIR data pipes. So this work started at in a collaboration with the OpenMRS community. So OpenMRS is like an EHR system that was originally developed for HIV tracking in developing world. But now this is back, I think, 2005, around 2005, where the work started. So it's widely adopted for these HIV programs, but it's now being used in many other, for other healthcare programs, including some national programs who have adopted OpenMRS as their platform for their national healthcare system. Then at the time in 2020, when we started collaboration with them, so the problem that we focused on solving was doing analytics, so how to do analytics for OpenMRS. But we didn't want to build a solution that is specific to OpenMRS data model. And the good thing was that at the time, at the same time in 2020, they were rewriting their FHIR interface. It's like this FHIR facade that Happy provides that you can put around your custom data model, and then it can talk FHIR. So when we said, okay, we build a tool that is, the first user, the first customer would be OpenMRS, but it would be a FHIR-based tool. So it basically talked to OpenMRS as a FHIR server. So that's how the work actually started. And from the get-go, from the very beginning, the goal was that it should be easy to use the tool on a single machine. In many places in these clinics, it's just one laptop that does everything. It's actually the EHR system for the clinic, and they didn't want to have a separate machine, for example. So it should be easily run on a single machine, but at the same time, the same tools can seamlessly be deployed on a cluster, for example, whether it's an on-prem cluster or whether it's a cloud, like a public cloud cluster. The same code should be scalable. So that was the goal from the get-go. And as I said, the focus was in general in low resource environments. Okay, I'll go through this very quick. We can come back to this in QA, but this is kind of the basis of our work. So the columnar formats are, we convert the FHIR data into a columnar format, and columnar formats have been around for a long time. It's known that they are very good for analytics queries. In analytics queries, so think about you have many columns in your table, but then your analytics query is usually like a table scan in many cases. So you don't necessarily have good indices on the columns that you want to query. But usually, let's say if you have tens of columns or hundreds of columns, you usually just query like a few columns. So you just have like a filter on 3 columns, for example, and then you have an aggregation on some other columns, basically. So if instead of storing my data record by record, I store it column by column, then I can do these kind of queries much faster, because the amount of data that I read is way less. And the origins of the open source implementation, which is Parquet that we use, goes back to the Dremel paper, which came out out of Google in 2010. I think the Dremel system itself started in 2006. But that work is actually the basis of BigQuery as well. So BigQuery, which is a famous service, analytics service that Google offers, is based on same concept. So if I want to summarize that, it would be 3 components. One is the columnar format. The second one is a distributed file system. And the third one is the concept of predicate pushdown. So if you look at this picture here, like at the bottom right, so my data is distributed on many machines, but then the predicates that I have in my query can be pushed down to any worker, and they just do the filtering right where data is, and then they just send a little bit of data that matches my filter, and then we do aggregation in a central place, or even the aggregation can be done in a hierarchy. So that's basically the basis of both BigQuery and also what we try to achieve here. Okay, so the big picture of what we do, and mostly I am in the transformation part. I'll talk about the query part in the second part of the presentation. So what we are doing is that, so this is the big picture. So we have like a FHIR server. We try to treat that as a FHIR server with some caveats that I'm going to talk about. And then we have 2 modes. We have a initial bulk transformation, which basically reads everything that we need for the first time from the FHIR server. And then we have a continuous mode as well, which basically, as the resources get updated, it just keeps reading the resources and then update the data warehouse. And the data warehouse is basically like, you can think of it as a set of Parquet files for now. So as I said, Parquet is the open source equivalent of what Dremel was trying to do. And using Parquet as the format is useful because many tools understand Parquet. Yeah. Sorry, Dremel? Yeah, Dremel is similar to BigQuery basically. So basically being able, so if you know, I remember like 2010 when I was, you know, it was my first year in Google, everybody was excited about this tool that you could write a query and then run, let's say, on, you know, billions and billions of records in a few seconds of, you know, let's say, you know, ads click data, for example, right? And people were excited. I was not there before. People were excited because before they have to run like a map reduce, or there was a specific language called Sawzall, which was translating into map reduce. And the same job could have taken like, I don't know, maybe an hour or something. So then this was a, you know, a paradigm shift, because you could sit at a console and then do data sciencey type of thing with, you know, your record, like, you know, all of the clicks, for example, for yesterday. So that was basically what Dremel was trying to do, which is the basis for BigQuery as well. But yeah, I was saying that, you know, Parquet is, the nice thing about Parquet is that there are many tools that understand Parquet. So we have a proposed solution how to query the generated data, but obviously people can choose anything that can understand Parquet. So, and that's actually another feature, which makes the two parts kind of separate from each other. Okay, and then the vision that we have is not limited to Parquet. We have actually done some preliminary experiments. So we want go even beyond Parquet, and we have the option of different, you know, quote unquote data warehouses. It could be just like a normal database like Postgres, for example. We have heard strong feedback that, you know, my data is small, don't force me to use the Spark. I just want to use Postgres, right? And this is a very valid feedback. So that we have actually done some analysis work to support Postgres as well. We want to, you know, support BigQuery, you know, as a first class. I mean, there is a way now to use BigQuery as well, but we want to support as a first class citizen. But then also for the query part, we want to do more. It's not just that, you know, showing people how to query, but we want to be able to actually implement some, you know, standard metrics, for example, support for interactive queries. Like, for example, if we have CQL to SQL, that's also something that, you know, eventually we can support, and obviously, you know, dashboards. Okay, so what is horizontal scalability? So let's clarify this a little bit, because different people mean different things by horizontal scalability. So I would say there are two types of horizontal scalability. So basically, what horizontal scalability is that if I have a performance problem, I can add more machines, and then my performance problem is gone. So it's very simple to say that, but actually having a system that actually can perform that way is actually very hard. It's not simple. You know, both for transactional systems and for analytical systems, doesn't matter. Because, you know, having the same code that runs efficiently on a single node, being able to scale, you know, in a distributed way on many nodes is actually not an easy thing to do. But then this is the generic part. The two types are, so when you have a, let's say, a transactional system, so like, you know, like a web server, and I have many queries coming. Each query takes just a few milliseconds to perform, but I may have billions of queries per second, for example, right? So that's one type of horizontal scalability, where I have many small queries. Another type of horizontal scalability, which is, you know, for analytics queries is the case, is that I have very few queries, like one single query that needs to go through billions of records, right? And I want that type of query also be horizontally scalable. So that single query, if it's slow, I just want to add more machines to my infrastructure, and then that becomes fast. And why is this important? Because of that, you know, paradigm shift that I was talking about with Dremel. That, you know, we want people like data scientists to be able to sit at the healthcare data, on top of the healthcare data, you know, do their analysis, and then it's being interactive. That's usually when you get insight. You know, you do a SQL query, you change something, you get feedback, new results in a few seconds, and then you just improve. Okay. And this one also, some of the content on the slides, I will try just to go through really quickly, and then we can come back to them in QA. So SQL on FHIR, you probably have heard multiple times, like Payet has a talk yesterday. He talked about SQL on FHIR, and Nikolai, for example, talked about SQL on FHIR v2. And So the SQL on FHIR schema that we use here is the V1 version, which is basically like, again, I don't go to the details of it, but it's basically like a projection of FHIR resources into like a SQL schema. So you can think of it, divide all of the fields that I have into columns. You can think of it that way, basically. I mean, there are obviously nuances. And so it doesn't need any documentation because its documentation is the FHIR documentation. So it has a high fidelity. Like the example that I'm showing here is that on the left is the patient from the FHIR website. And then, we have like identifier, we have name, we have telecom. And then this is the BigQuery version of SQL on FHIR. On the right side, you can say we have similar things like, identifier and name. And for example, name is a record, like name here is like a human, you can see my pointer, right? Name is a human name here. And then basically it's a record on the SQL on FHIR side, and it has different fields that it have. It can have like a family as a string and so on. So this is the format that we want to transform our data to. And why is that? I mean, by now it should probably be obvious, because we want to store our data in a columnar fashion, right? So we don't want, I will talk about JSON at the end, but we don't want to do just JSON. So we want to actually divide our data into columns and then store them in a columnar fashion. Okay, so the pipeline that we have for transformation, basically, what it does is, it talks to the FHIR server in different modes, read the resources, transform them into Avro records, and then Avro records, it's very simple to store them as Parquet. So it's basically, it's based on this Bunsen library, which I think originally, I think both SQL on FHIR and Bunsen, at least one of the co-developers of both of them was Ryan Rush, who is currently at Google, and if the timing was right, he would probably be co-presenting with me. He's in a different team right now, but back then he was in Cerner, and this Bunsen library is an open source project under Cerner, but it's not being maintained anymore. So we have to fork it on, the pieces that I needed, we have to fork it under our repo. That's the basis for doing the transformation. What it does is that it reads the structured definitions for FHIR resources, create Avro converters based on them. So with that, we just read a JSON record, convert it to an Avro record, and then write it into Parquet. And we have implemented with Apache Beam. Again, I don't want to go to details of it, but basically it is a pipeline like interface library. So it's a way for defining data pipelines, which is independent of the runner. So you just say, what is my pipeline? And then the nice thing about it is that there are many runners for it. You just say run it on a Flink cluster, run it on a Spark cluster, run it on a Dataflow cluster. It's just like configuration parameter, but it's the same code. Okay, so it has different modes, and here are the details that then we try to work with the standards, but not always. So the first mode that we have is using FHIR Search API. And the reason that this was the first mode that we implemented is kind of historical. So this Search API was what being supported by OpenMRS at the time. So OpenMRS doesn't have like this FHIR bulk data export, for example, right? So that's the first mode that we implemented. It is still supported for a small amount of data. That's totally fine. There are issues with pagination, there are very little guarantees. If you read the FHIR spec, there are very little guarantees about pagination, and you may get inconsistent data. Some, depending on the FHIR server, some provide better guarantees, some less, but the actual spec is very minimal. And also we had issues with the scalability. Again, I can talk about the details of it. But the main mode that we use for local deployments is the JDBC mode. And this is the one that is not a standard anymore, because it's actually talking to the database that is backing the FHIR data, right? So it's directly talking to the database. So far we have implemented it for, the first thing was OpenMRS, but it's also now supported for Happy, which is nowadays is the main user. Basically, like our partners mostly use Happy FHIR. And we have implemented this mode that directly reads from the database, and the resources are stored as like gzip resources in Happy. But of course, in next version of Happy, they can make a decision to change their internal data model And our data pipeline needs to be adopted as well. So that's the bad side. And then it has different write modes. It can write into Parquet. I talk about support for other data warehouses, and also it has a mode to write to another FHIR server. It again comes from a historical use case that there were many OpenMRS instances, and they want to integrate the data in a central place. Okay, and just 2 sentences about continuous updates. I don't want to get again into too much details. We started with so. We plan to use FHIR subscription API, but we haven't done that yet for different reasons, like OpenMRS didn't support it at the time. There is significant difference between R4 and R5 in the spec itself, so we didn't want to build it on top of something that is being changed. Or there is a streaming mode like for OpenMRS that uses Debezium, and Debezium hides the database, but it's still, the data model is still there, so it's based on the data model. But then we also have a micro batch mode, which is generic, like it can use with FHIR search. And the way that it works is that you just schedule it for being updated every 1 hour. So every 1 hour it fetches new resources, any resource that has changed since the last hour, it fetches them and then merge them with the old one and generate new Parquet files basically. Oh, it was actually way more than 2 sentences. So this one I really want to skip. This is the synthetic data that we are going to, the performance numbers that I'm going to talk about is based on this synthetic HIV data. I can talk in QA if there is interest on how this data is generated. It's based on realistic data that was coming from OpenMRS, but obviously it is synthetic data. There's no real patient information in it, but the probabilities are from there. There are 3 sets that I may reference here. There is an 8,000 patient set, 80,000 patient set, and 800,000 patient set. In each of these sets, each patient has about 200 observations, right? So just have those numbers in mind. So when I talk about the 800,000 patient data set, it means we have 170 million or 160 something million observations. So that's the scale that we are talking about. Okay, so before going to the query, some performance numbers about the pipelines. And for this case, I'll just talk about the single machine use case. So everything is on a single machine, like the happy FHIR server, the Postgres, and the pipelines are all on the same machine. The machine is a really good machine. It has 48 cores and it has close to 200 gigabytes of RAM. And most importantly, it has an SSD, which is probably the most important thing in this context, but still it's a single machine, right? So in this case, it will take, the throughput of the pipeline is about 2,200 resources per second. But really it's not much about the pipeline, and that's why I have included this graph here. So it's the CPU usage of different components. The green is the database, is the Postgres. And then these 2 are the pipeline and the happy server. So these 2 are basically nothing compared to the data. So very quickly, the database becomes the bottleneck. Now, if we don't have that as the bottleneck, if the database is not the bottleneck, you can go up again on a single machine. You can go 60,000 plus resources per second. This is where we read from files, right? And if you have, like, let's say, if we were using bulk data export API of FHIR, we would have this scenario, because it would become the responsibility of the FHIR server to generate the JSON, ND-JSON files for me, and then we will just read from them, right? So this is like more realistic if you want to analyze, how the performance of the pipeline is. But in the case that we are directly reading from the FHIR server, or even like the database, the database itself becomes the bottleneck. We can talk about horizontal scalability for this case in QA if there is interest. But let's go to the query part, such that I have enough time. So for the query part, again, as I said, people can use any tool that understands Parquet, and there are many tools that do that. In here, from now on, I'm specifically going to talk about the Spark, which obviously understands Parquet, but it can also do the job of horizontal scalability for us. And then from the get-go, from the very beginning, that was actually our story about horizontal scalability of the query part. that you just deploy, you just copy your files in a Spark cluster, and then everything would be basically done with horizontal scalability will be done by the Spark cluster. So basically you have like a master node, you have some worker nodes, and then we have a thrift server, which is like a JDBC connector, and it's also like a Hive meta store. I mean, we don't need to get into those details, but basically what you can do, I mean, from a user's perspective, you have an endpoint to which you can send SQL, right? So everything is done with SQL. Regardless of how basically, that's our vision, regardless of what query engine you use, we want the end user to actually write SQL. And again, on a single machine setup, this is much simpler. Like, all of these, I mean, in the afternoon, we have a let's build session, and then everything here basically goes into one component, which is, just one process in the single machine mode. Okay, now also for the query, this would be my running example. So I will use this, this TX new comes from these PEPFAR indicators. So PEPFAR is, I think the acronym is President's Emergency Plan for AIDS Relief, something like that. So that was the programs that were funded, the HIV programs that were funded by USAID. There was some requirements about reporting, like, that, how many patients have been admitted, how much drugs have been used and things like that. So it's like a 200 pages PDF document that actually define tens of metrics that needs to be implemented by these programs. And this TX new is just one of them. I just picked it. I just wanted to have a realistic example. And this actually comes from the community that was the first adopters of these tools. So this is basically to count number of patients who have been admitted into an ARV plan and the antiretroviral plan in the last period, for a single period. And this period can be a month, a quarter, or a year. So usually we deal with value sets, but in this case, it's a very simplified example that I have just one value. So I have one value for the ARV plan, which is 1255, and I have one value for the observation value, which is the start drug, which is 1256. And also, why this is in an observation resource, you can argue that this is not the right way to model the data, but this is how OpenMRS models it. So it's not my pick. Okay, so what we usually do is that first so what is the problem for writing these queries? The problem, I mean, when we tell people, okay, you know SQL, right? And they say, yeah, we know SQL, then you can't just say, okay, so you can write SQL for this data, because we are dealing with nested columns and also repeated columns, right? And that makes it usually, that SQL is a different type of SQL. Like, and for me, it actually took a long time to actually be comfortable working with that SQL. And even, at the time I was working mostly with BigQuery and Dremel doing that. When I switched to Spark and doing the same thing, I knew the exact concept, but just figuring out this, lateral view explode thing, which is just the same thing I was doing in BigQuery, doing it in Spark. It took me again hours to figure out what is the exact semantics. So there are details here how to do this, but the basic concept is that if I have a column which is repeated, so let's say I have 5 codes with different code systems, right? I can repeat that row 5 times, and then that column becomes a single column. It's not repeated anymore. And each row has one of those values, right? So that's the basic idea of flattening. And that's what I am doing here. So I'm doing the flattening on code.coding, and I'm also doing flattening on the values when it's a codable concept and the coding. So I do this flattening first. I'll just go through this really quickly. I get a very nice flat view. So this is the view that I get from my observations. And then this is easy to work with. And this is the data I want. So these are only the codes that I'm interested in. And now I can join this with patients, and I can get patient demographic data. So I skip these just for time. These are some performance numbers. So that query, doing it on the 800,000 patient data set with 160 million observations. So the join is actually usually the heavy part. So on that local, like 20 core, so I have limited the Spark cluster to just 20 cores, but the machine has 48 cores. So the cores were used for operating system and other things had more cores. But then it's done for that data set, it's done for about 69 to 71 seconds. And then CPU utilization is very, very high. And these cases are doing exact same thing on a cluster. And the cluster in this case is like a data proc cluster. So I haven't tried to optimize it at all. I just have clicked on Google Cloud Console and then created a Spark cluster. So with 5 nodes and 4 cores each, it's actually slower usually than the other one. And the CPU utilization, you can see it's lower because it's, the data is not necessarily sitting at the same machine that's doing the work. So the data is also in a distributed file system. And exactly doing the same query with 50 nodes each with 4 cores, I can get a little bit better speed up, but again, CPU utilization goes down. Okay, there is a section on why not JSON that I am going to totally skip, but we can talk about it in the QA part. There are performance issues, and it's actually a legitimate choice, but there are caveats about it. So I skip these, and I quickly talk about these flattened FHIR views, because this is actually something that I really want to cover briefly, at least. So the idea is that the same concept that we did by defining this flat view with my SQL query, what if I generalize it and then it's not dependent on a Spark anymore? And then that's the idea behind this FHIR views. So if you go to this link, this is the FHIR views. This code is open source, but it's the open source by a different team in Google. It's actually Ryan Brush is the lead for that team. So the idea there is that instead of using the right-hand side, SQL here, and then this is a specific to the query engine, what if I use FHIR path to define my view? So make it independent of the underlying query engine and even underlying format. Use FHIR standard concepts to define the view that I have. So I want, let's say, ID, and I want the patient ID from observations, and the constraints that I have is that this code is actually, and then here is great support for value sets as well. I can set from it's a member of this value set, and then the reporting period is like 2010. So the left-hand side becomes the right-hand side basically, but then this is done by the runner. So the vision is that we have one view definition, and then we have different runners, so similar to the beam concept. And then different runners compile that view definition from FHIR path into some way of running it on the query engine. So currently the original implementation was for BigQuery, which Ryan's team did. One of my colleagues in the Open Health Stack team has done an implementation for a Spark as well. And I think supporting JSON and maybe Postgres is also in the roadmap as well. So yeah, so I just skipped this one, and yeah, this is my contact information. And as I said, there's a Let's Build session in the afternoon. Sorry, I have to run through this very quickly, but hopefully I can answer some of the questions now.
Thank you, Bashir. Any questions?
Quick question. In that slide where you were showing that architecture from Postgres for the Happy, did you use Kafka in the middle to get from Debezium into Kafka, and then from there you were reading it, or was there something direct there?
Yeah, so for, maybe if I just use this, it's probably easier. Just good to go that. Yeah, so yeah, for this one, I mean, when we are, so in the bulk, so there are 2 modes, right? In the bulk case, it's just directly Unity. And then in the continuous mode, so we have implemented for OpenMRS, but that is based on Debezium. So it basically, we don't use Kafka. So basically, it directly reads from Debezium messages. Basically, it's based on Camel, but those are details. But that basically reads each update that Debezium reports. It contacts the FHIR server. So it just picks the ID of that resource. It contacts the FHIR server and then gets the FHIR server for that ID again. So it's basically like a stream of IDs. You can think of it that way, but it doesn't use Kafka.
The reason I was engine or was it for the pipeline's performance?
So I showed two performance numbers. One, so the question is about the performance number that I showed. This one was these numbers were for the transformation part, which is where when we are transforming the data from the FHIR server into Parquet, and then after we have the Parquet, then the FHIR server is out of the picture. The other number that I showed were these performance numbers, which are the Spark queries, basically, right?
Any more questions? If not, we can have some questions from the Whova channel. How do you know the resource changed?
Sorry?
How do you know the resource changed?
Oh, okay. So the change in the resources, yeah, the interesting question about the streaming mode. Let me just bring up this slide that I had for, streaming. So there are different modes. Like I said, we have a micro batch mode, and then we have a streaming pipeline. So the streaming pipeline is mostly, as I said, for OpenMRS. The way that we know a resource has changed is by listening to DBZM. Like, if I have like MySQL, for example, there is like a bin log that, records any resource that has been changed. But DBZM basically hides these details for us. So it's basically we have a stream of events which are change events. And what we do is that we just extract the ID of the resource that has changed. So we know that if this patient table, this row has changed, it means that I have to fetch patient.id again. So that's basically how we know. The other mode, which is the micro batch mode, in that mode, what we do is we use the since, or I guess last updated. I mean, if you are using the bulk API, you use the since query parameter. If it's just using like, search, for example, API, you use the last updated. So we know when was the last time that we ran the pipeline, like last hour, for example. And then we say everything that has changed since last hour, report all of those to us. And that's how we know which resources.
Thank you. Another question, does FHIRPath take input as code in Parquet and create a view?
Sorry, can you repeat that?
Yeah, does FHIRPath take input as code in Parquet and create a view?
I'm not sure about the part as code in Parquet, but so basically the FHIR path definition, I'm guessing, so let me make sure that, I mean, at least tell you which question I am actually answering. So I think the question is like, these FHIR paths that we use here for defining the view, is it, getting anything from the Parquet file? And the answer is no. So like, I mean, this definition, this view definition is supposed to be dependent only on the FHIR resources, right? So it's agnostic about how I am going to actually run this query, right? It's all about FHIR resource. So we just say, so these are all like, FHIR concepts, regardless of whether I'm actually storing JSON resources in Postgres or I am, storing my resources in Parquet and I'm using Spark for querying. I just say here that, I want patient ID from each observation. I want the status of it and, the effective time. And the constraints that I have is that, that observation code is a member of this ARV value set. So all of those are just dependent on the FHIR resource. And then what happens, depending on what query engine we have, this is translated into like something that is, this is basically a Spark on using Parquet and SQL on FHIR, basically. So the flow of information is just one way. Yeah.
Thank you.
So if there is no more question, then I will use actually a few minutes talking about the JSON part very quickly because I skipped this one. And I think we have, if I'm not mistaken, we have 3 minutes left, right? Something like that. 4 minutes, yeah. So let me just go back to this slide and then quickly talk, because this come up frequently that, okay, I just want to use JSON and why not JSON, basically, right? So we did some experiment. This is actually, the first thing is that, this is actually can be a valid option. So I'm not going to, so what I'm going to present doesn't mean that, no, this is a very bad option, right? But I am going to focus more on the problems and why we haven't gone with JSON yet. And even if we go with Postgres, it's very likely that, we use a kind of like a schema, like a SQL schema. And again, we can talk about the details of it. But the experiments that I am going to talk about uses a very simple schema, which is I only take the ID and the type of each resource. And then I have, we can ignore the data column. It's just JSON. I wanted to compare raw JSON with JSON-B. And obviously, the performance of the raw JSON is actually terrible. But Postgres has this JSON-B, which is very, way more performant compared to just raw JSON. So actually, they have done a good job implementing JSON queries. And SQL has support for JSON as well. So nowadays, you can actually write queries like this that you say, so this data B is my FHIR JSON resource. And you can say that, my, let's say, observation, subject, and reference, I want to get that. So these are these, operators like, path operators. I want the code. And then you can also do the same thing, like, the same flattening idea that I was talking about. You can do it here. You can just do a cross-join lateral, which means just, in this record, explode this JSON array, for example, for me, the same concept, right? I can do the same query, the same view definition. And then I can also have constraint. I can say that, this code that I have here should be this value, which is for ARV plan, and then a start drug, right? So I can write the query support for it in SQL, in JSON SQL, and then I can also store my data as JSON, right? And then this becomes the whole query, the same TX new query, this becomes like that. Now, what are the problems? So the problem is that sometimes you can get into performance, big performance problems. And this is one example here. Yeah, and this is one example here that we have. So the join criteria is joining between the patient ID and the observation subject patient ID, right? This is the join criteria. And this is usually the most expensive part. For Parquet and Spark, it's also the same story. Now, writing the query this way, I had a really hard time, and this is just with the small data set, it's with the 8,000 data sets. So it would take tens of minutes to run this. And I have slides at the end in the appendix, if you look at the slides online, that I have actually analyzed the query plan. And it shows that it's actually doing a nested loop join here. Even though I have actually created a B-tree index on this ID. So even if I tell the database that, create a database, it doesn't use it in this case. If I just turn off cross-join, so there is an option in Postgres, you can say never use cross-join, never use nested loop join, just that. Then it becomes tens of seconds doing the same thing. So I don't make any changes. I just tell the query engine, please don't do this. Please don't use nested loop join. You have better things to do. So these are the issues that you need to play with the indices. You need to be concerned about the query plan and how things are being done. And I guess I don't have a good solution right now for them. While in Parquet and Spark, you can create indices for Parquet, but we don't. There is no indices. And whatever column the data scientists want to use, they can just use that. And it's much simpler to use. Okay, thanks again, everybody. Yeah.